Good morning, class. We are looking at exam 4 review, which covers from section 4.4 to 5.4. Many integration formulas. Hopefully by now everybody is comfortable with them, so we can move on. These are some examples of optimization problems. Find two numbers whose sum is 54 and whose product is the maximum. Number two, a farmer wants to fence a rectangular field beside a river with 2,400 feet of fencing. The river itself will be one of the four sides. What dimensions will give the largest area? Number three, a box with a square base and open top must have a volume of 5,324 cubic centimeters. Find the dimensions that can minimize the amount of material needed, probably for minimizing the cost. If 5,400 pi square inches of metal is used to construct a cylindrical storage drum, what is its maximum possible value? So these are some examples we come across. The best thing is to come up with the setting and draw something. As you can see here, I'm going to look at question number 2. So we want to maximize the area, which is x times y. And the constraint is the perimeter, which is normally 2x plus 2y. In this case is 2x plus y. We have 2,400 feet of fence. So this is the objective function. This is the constraint, everybody. We are going to solve for y. So that's the first step. That's the second step. And we are going to replace the y in here. X times 2,400 minus 2x. The reason x is between 0 and 1,200 is because x represents a dimension must be positive. At 1,200 makes the second parenthesis 0. And if you choose larger than 1,200, the second parenthesis is negative. The area becomes negative. That's why we have this open interval of 0 to 1,200. So area is 2,400x minus 2x squared. We differentiate and we set it equal to 0 to find the critical point or points. X becomes 600. The first or second derivative test is done. In this case, the second derivative is negative, which means concave down this way, concave down, and that means the maximum occurs at that vicinity. So if x equals 600 will give us the maximum, we can go back and find the y here and the area here. So this is how you tackle an optimization problem. Initial value problem. It's important to understand this is really a pair. This gives us the following pair 0, 3. 0 is the value for the independent variable, which is normally x or t or theta, and 3 is the value for the dependent variable. Let's multiply both sides by dt. Let's integrate. So the left side becomes v of t, and the right side is very simple. This one is minus e to the power of negative t. This is itself e to the power of t and a constant. This is the general solution class. Now we are going to plug this in to find the value of the constant. Please understand, when we replace the t with 0, this becomes e to the power of 0, which is 1 with the negative sign in front of it. This is negative 1. This is positive 1 and a constant. Therefore, these two cancel each other. C becomes 3. Replace it here. And the general solution now gives us one solution, which is known as a particular solution. So the initial value will help us get one solution. We want to find all functions such that G prime is given. That means basically anti-differentiate or integrate. So here's the hint. Sometimes we have to simplify, factor, cancel, remove radical notation. Sometimes we have to do substitution. So this is 1, and this is another one, the second fraction, where square root of x is x to the power of 1/2. We rewrite this as such. We integrate to find g of x. Needless to say, when we are integrating, we tag along the x. The derivative of sine is cosine. The integral of that is negative cosine. So minus 4 cosine x plus 2 over 4 plus 1 is 5. 2 over 5x to the power of 5 minus 1 over negative 1/2 plus 1 x to the power of negative 1/2 plus 1 and a constant. Now this is 1/2. So is this one? 1 over 1/2 gives us 2. So negative 2x to the power of 1/2, which is the square root of x. And that's the final answer. Fractional expression, more specifically here, we have rational expressions because the top and the bottom are both polynomials. The first step is to simplify if we can. This cannot be simplified. Let the denominator be u. The derivative of the denominator is 4x plus 1. So du is 4x plus 1 times dx. Rewrite this expression and you end up with the integral of du over u, which gives us a natural log. And we replace the u with 2x squared plus x minus 3. This is the final answer. Pay attention to the fact that we need to use the absolute value sign because this expression can be positive or negative. In part B, we want to do the same thing. However, we can simplify it first by factoring out the x minus 1. This cancels out x minus 1. And it looks like that. 4 over 2x plus 3. Now, if we let u be the denominator 2x plus 3, the derivative of 2x plus 3 is 2. So we have 4 times dx. Du is 2 dx, so this is 2 times that. That's fine. So you can write 4 as 2 times 2, or just take it out, multiply by 2, divide by 2. That results in 2. Either way, this is the answer now. And the next step, this is the natural log. U is replaced with the choice of u, which was 2x plus 3. And again, we need the absolute value sign because 2x plus 3 can be positive or negative. I want to look at the same thing as B, except it's reciprocal. The reciprocal of this class can be again factored out to reciprocal of the green piece, 2x plus 3 over 4. This time, after simplification, we notice we have one fraction, 2x over 4, which is 1/2 x. We have the second fraction as 3/4. Therefore, there is no need to do the substitution. 1/2 x, x gives you 1/2 x squared, so that's 1/4 x squared. I hope everybody understands what's happening. X gives you 1/2 x squared. Let me just write this part, everybody. Gives you 1/2 times x gives you 1/2 x squared. Therefore, you have 1/4 x squared plus 3/4 x and a constant. This is similar to what we did. We've done it in the previous section. We are looking at a fractional expression here, a rational expression here. The first step is to simplify if we can. Since we cannot, let u be the denominator. I hope you realize the derivative of the bottom is the top. So du becomes e to the power of t dt. So the expression becomes the integral of du over u, and that results in a natural log. Now replace the u, and we're done. Because the expression is always positive, you could use parentheses, class. By the way, if for any reason we don't see what's happening here, we can rewrite this as the integral of 1 over u times du, if that helps. You don't have to. The second part, we want to simplify. First and foremost, it can't. We go through the process of setting u to be the denominator, and du is 2x plus 2, or 2 times x plus 1 dx. So I hope you remember what we did. Number 2 is missing. It is a multiplier. We can multiply and divide by. So pay attention to what we do here. We just throw in number 2. That means we are multiplying. To undo it, we divide by it or multiply by its reciprocal. Again, this gives us natural log. Replace the u, and we are done. This has to remain in an absolute value because the expression may be positive or negative. And again, I wanted to show you the reciprocal of this. We can cut it into 2 fractions. We did that before. This is 1, 5 e to the power of negative t. This is another one which is simply 1, and you don't need to use the substitution method. And we're done. Remember, in the case of integration, we are dividing by -1. It so happened division or multiplication by -1 makes no difference, okay? We are dividing by -1. All right, for a case like this, the first one, just pay attention to this, which means you should know what's your independent variable. The reason I mentioned that, sometimes students write 5x or 5t, which is wrong. 5 theta. The derivative of cosine is negative sign, but the integral of cosine is positive sign. So 5 theta plus 2 sine theta, and of course, a constant. Anytime we have an exponential, most likely it is the exponent that is the choice of u. When we do that, and we move x to the power of 4 next to the x, notice number 5 is missing. We multiply and divide by it because, as I mentioned, in the text, they solve for the x. It is much easier not to. Instead, notice a number is missing, you can multiply and divide by. Now this one is 1/5 e to the power of u, and a constant. U is replaced, and we are done. Dealing with sinusoidal functions. If the argument is being raised to the power, that is the choice of u. If we do so, du becomes 2x dx. We move the x next to the x. We notice 2 is missing. We multiply and divide by it. So because it's a number, it's not a big deal. Again, understand the product of 2 and 1/2 is 1. The derivative of sine is cosine, but the integral of sine is negative cosine. Replace the u. We are done. We can always check by differentiating the result. Should give us x sine x. In part B, it is sine that is being raised to the power. And by the way, whether it's sine or cosine, it doesn't matter because the derivative of sine is cosine and the derivative of cosine is negative sine. Pay attention to this negative and positive and you can make it work. So we let u be sine, du becomes cosine x dx. So simply rewrite this as the integral of u squared du becomes the power rule 1/3 u cubed and a constant, and u is sine x. The answer is 1/3 sine cubed x plus a constant. Let's go with a couple of examples I'd like you to do at home. The integral of sine to the power of 100x cosine x dx. Try this. Number 2, the integral of cosine to the power of 100 x sine x dx. So that's a good practice. Very simple, but it's worth looking at it. The integral of sine to the power of 100x cosine x dx, the integral of cosine to the power of 100x times sine x dx. We are using substitution for a definite integral. The result, we know it's a number. So let u be 25 minus x squared, du becomes negative 2x dx. We notice if we put the x next to the x, we need number negative 2. We multiply and divide by it. The product of negative 2 and negative 1/2 is 1. They are reciprocals. We can write now the u substitution. I'm not going to put the limits yet because there are 2 ways to handle finite, okay, the definite integral by going back to the original variable x and original limits 3 and 4. We're going to do that, and then the second method is explained. U to the power of 1/2. We have done this integration many times. This part gives us 1 over 1/2 plus 1, u to the power of 1/2 plus 1. 1/2 plus 1 is 3/2. 1 over that is 2/3. With negative 1/2 gives us that. So we can go back to the original variable. Therefore, we are going to replace the u with 25 minus x squared, and we use the old limits. However, we can put number 3 here, which gives us 25 minus. Now 3 squared is 9, and 25 minus that is 16. If I put the 4, I get 25 minus 4 squared is 16. 25 minus 16 is 9. By the way, do not mix up these two. Okay, the left side is negative 16 and the right side is always positive 16. So the negative sign is outside for this case. We can write it as such and replace the u. As I mentioned it before, this is square root of 9, which is 3. Cube it, you get 27. Square root of 16 is 4. Cube it is 64. 27 minus 64 is minus 37 times negative 1/3 makes it positive. Dealing with ln x, if you recall, most likely that is the choice of u. So let u be ln x, du becomes 1 over x dx. If you can see the result, fine. If not, rewrite this so it becomes obvious what you have by rewriting the components here. So we are separating. And by the way, dx over x or 1 over x dx, they are the same. So you have the integral of u squared du. Using the power rule, we get 1/3 u cubed plus a constant. Replace the u with ln x. We are done. A fractional expression. Try to simplify. We cannot. Notice the derivative of the bottom. Okay, e to the power of x is e to the power of x plus e to the power minus x is minus e to the power minus x. So the derivative of the bottom is the top. So if this is u, this 1 times dx is du. And therefore you have the integral of du over u, which is resulting in a natural log of u plus a constant. Replacing the u will give us the final answer. Let's look at an application. A bacterial colony increases at this rate. R of t is 2.2 e to the power of 0.4 t bacteria per hour. The initial population is 800. At t equals 0, this is what we have. We want to find the population after 12. So R of t is the rate of growth, and the accumulated change simply becomes the integral of this function. The amount of increase becomes the integral from 0 to 12. So we divide 2.2 by 0.4, because remember, with differentiation, we multiply by 0.4. In this case, we divide, which is the same as 22 divided by 4, giving us 5.5 e to the power of 0.4 t from 0 to 12. Now, this one, class, you have to evaluate. You plug in 12 minus you plug in 0. When you plug in 0, you get 5.5. And it's about 663 because it represents the number of bacteria. We want to round it to the nearest integer or whole number. So this is 663. We also had 800 to begin with. So we're going to add them up, and this is the final answer. The second method is, instead of lowercase r of t, notice we can calculate capital R of t, which represents the population at t, with the initial value R of 0 being 800. So we can do that. With that being the case, We've done the work here. So we can say capital R of t is this plus a constant. Okay. We've done the work here. Now we use R of 0 equals 800. That means we replace the t with 0 and we find the constant. I hope you realize. So this is the capital R of t. When I plug in t equals 0, this becomes 5.5. And C, they add up to 800. So it's 800 minus 5.5 or 794.5. So R of t becomes this plus, now we know the constant. What do we want? R of 12. R of 12 is the same as what we got here. So there are two ways to tackle this. I'm going to look at one more example that we did in section 5.4. The rate of growth of a fish population was modeled by this equation, where t is measured in years since 2000, lowercase g in kilograms per year. If the biomass was 40,000 in the year 2000, what is the predicted biomass for the year 2020? We are repeating the same concept, meaning the rate of growth is given. So if we want the amount of growth, we use the net change theorem. We take the integral of that because we go from the year 2000 to 2020 from 0 to 20. That's what we need to do. This is the amount of increase. We've gone over that, so I'm going to quickly recover that for you. This is the choice of u. And I hope you realize if you want to differentiate this, this becomes 5 times minus 0.6, which gives you negative 3 e to the power of a negative 0.6 t, and we multiply it by dt if we want to look at du. So this is u, this is du. This is number 30,000. We want negative 3. It's the product of negative 3 and negative 10,000. Now we go to the u substitution. If I put number 0 here into the u, this becomes 1, 1 and 5 is 6. If I put number 20 instead of t, becomes 1 plus 5 e to the power of minus 0.6 times 20, which becomes negative 12. And that's how we arrive at the lower and upper limits. So this is negative times negative. I'm hoping we've done this differentiation many times. Everybody knows how to arrive at it. So it's positive 10,000 over u, or 10,000 times 1 over u. The upper limit is almost 1, so 10,000 times 1 over 1, which is 1 minus 1 over 6. And using a calculator, an approximation is this much. We initially had 40,000, add to it. And that's the final answer for this question. As I mentioned before, we have a second method. We've gone through the process. We came this far. From here, the integration gave us this one. Therefore, capital G of t is 10,000 over u, 1 plus 5 e to the power minus 0.6 t plus a constant with the initial value of 40,000. G of 0 is 40,000. You can replace the t with 0, which makes it 10,000 over 1 plus 5 plus c equals 40,000. Find the missing constant. This becomes your equation. And after, for the first 20 years, we want t to be replaced by 20. So this is the general formula representing the total biomass at any time t. G of 20 is calculated using a calculator to be 48,333 kilograms